this section, we're going to learn about optimization. And optimization is a process of finding absolute extrema, sometimes minimum, sometimes maximums, but we're looking for these over a specified interval. And we have already learned how to optimize functions in general, but these are problems that are subject to some sort of constraint. And I'll show you what I mean as we go in through some examples. Usually these are all word problems. If you'll notice here, I put the word real-world applications in quotations because, I mean, let's face it, they're not real-world applications, but they are simple enough applications to get you to understand the fundamentals. Because the thing is, the actual real-world applications are either A, proprietary, or B, so difficult that it's hard to get you to understand fundamentals of what you're trying to learn here. So we use some basic things and learn fundamentals from that. Starting with a classic problem here, the old man in the garden. So an old man wants to build a rectangular garden and has 180 feet of fencing to do so. What is the area of the largest garden that he can create? Okay, so the thing is, there is something that we want to either maximize or minimize. And you have to generally first decide that in the problem. So the thing that I want to maximize in this problem is area of a rectangular garden. And notice I'm really writing out everything here because a lot of times I have students who will say, I come to a word problem and I just don't know where to begin. And what I understand from that is generally they're trying to just pull numbers out of the problem and do something with those numbers, and that's just not going to cut it in mathematical modeling, what we're doing here. What you have to do is fundamentally understand your problem first. There's no way to, in general, learn how to solve problems without understanding the problem to begin with. And usually just rewriting the things that you're looking for is a great way of making sure you fundamentally understand what you're doing. Because if I'm trying to maximize the area of a rectangular garden, it doesn't matter that it's a garden, it's area of a rectangle that matters. So I have some rectangular situation, and the basic dimensions of rectangles are length and width, and I'm just going to use x and y instead of L and W. It doesn't really make a whole lot of difference. Those two dimensions multiplied together give me area. So I have a function, area is x times y. This is a function that I want to maximize. I've got a great start here, okay? Now, the problem is, if we were just maximizing area of a garden, well, he could pick any dimensions that he wanted. He could make 50 miles on one side, 1,000 miles on the other, but the problem is there's a constraint. He can't make a garden that large because he only has 180 feet of fencing to build this garden. So, with that in mind, we have to consider there's different size gardens that we could create that would be rectangular and use up all the 180 feet of fencing. So for instance, well, first I'm going to say my constraint is the 180 feet of fencing. And just working things through in my mind here of how this would pan out. So let's say I go and I start building a garden, okay? I make it rectangular, and I could have a garden that has, I've got to use up all 180 feet of fencing. So let's say, for instance, I have, oh goodness, 60 feet one direction, so that would be 60 feet this direction. and then that would be a total of 120 feet. That leaves me 60 feet altogether for the remaining sides. I probably should have labeled the other sides as 60. This is not drawn to scale, but here's a potential garden. I have two sides at 30, which is 60 feet total, two sides at 60, which is an additional 120 feet total, for a total of 180 feet used. Area of this garden is 60 times 30. So let's see, 6 times 3 is 18, then there's 2 zeros, so 1,800 square feet. So there's one potential garden I could use here. Alright, well, there's other gardens, and perplexingly, they would have different areas, different set of numbers here. And again, I probably won't have anything to scale, who knows. Let's say I have one side at 10 feet. Okay, so that would leave, that takes up 20 feet of fencing so far. And then that leaves me 160 left, so that would be 80 feet for the remaining sides. So that the total here would be 180 feet. Alright, so if that's the case, this area would be 10 times 80. 1 times 8 is 8, then 2 zeros. Wow, this is only 800 square feet. This is a significant drop in square footage. It's a much smaller area of garden than the other. So that restriction makes a difference. So we have to come up with the dimensions of the garden that's going to produce the largest garden that we can. So one thing you may have noticed here is this constraint of 180 feet of fencing. It has to do with the perimeter of the garden. It's the outside edge. Perimeter of a rectangle is 2 times its length plus 2 times its width. And that total can only be 180. That ties in our constraint here. So 180 equals 2x plus 2y. Or equivalently, if you divide both sides by 2, 90 has to be equal to x plus y, which if you look at these two that I did, 80 plus 10 is 90, 30 plus 60 is 90. The only way to get the perimeter to be a total of 180 is if those two sides add up to 90. Right? So that we can actually solve for one of the variables. It doesn't really matter which one. We could say y equals 90 minus x, for instance. And that gives me a relationship between the variables x and y, which is good because up here, this function that I want to maximize, it has two independent variables. X and y are both independent variables. The problem there is I can't really maximize something that has two independent variables given our techniques that we know right now. I can only have one independent variable. However, using this constraint, I can rewrite one of those variables in terms of the other. That's the key to solving these things. So if I want to maximize a equals x times y, subject to the constraint, y equals 90 minus x, then I have that the area could be found using the formula x times 90 minus x, or the area is 90 times x minus x squared. This right here, this is a single independent variable. This is just like any other function that we have. looked at so far in the class. If I want to maximize this particular function, all I need to do is take the derivative of this function, which would be 90 minus 2x. And we know that if we set derivatives equal to 0, we find locations of minimums and maximums. So I could set this equal to 0. That lets me know that 2x would have to be equal to 90, or x equals 45. Now, at this point, it's probably instructive to know whether or not this is a minimum or a maximum. Generally, that's easy to tell. I usually will go for the second derivative test here, because the second derivative test will tell me very quickly. So for instance, if I get the second derivative of this function, my second derivative is -2. So it's a constant value that's negative, and anytime you're on an interval that's negative, you are concave down. And if you're concave down, anytime you would come across a critical value, that value would have to be a maximum. So that tells me that this point right here would maximize area. But it's not a point yet, it's just half of what I need, because I've got 2 dimensions to the garden that I need to create, and I have to calculate what the other dimension to the garden would be. So that's simple enough. We know that y is equal to 90 minus x, and when x is equal to 45, we can say y is equal to 90 minus 45, which is 45. So the dimensions that maximize area are x equals 45 and y equals 45, and that maximum area is 45 times 45, and 45 times 45, just grab a calculator to figure that out, 2,025. So 2,025 square feet in this case. That's the largest area of rectangular garden we could produce. Here's another example. What points on the graph of y equals 4 minus x squared are at a minimum distance to the point 0, 2? Right? To get a full understanding, it's good to have a picture of what you're trying to determine. It's good to try and write out what you're looking for. These are the kinds of things that you're trying to come up with. Write them down first, understand your problem, then try and solve. So what we're trying to do is we're trying to minimize the distance from the point 0, 2 to the function y equals 4 minus x squared. Okay. If we want to look at this as a picture, you could graph y equals 4 minus x squared, which it's a parabola facing downward, but I'm going to do it on the calculator just so we have a nice accurate picture here. So 4 minus x squared, if I graph that, okay, and let me just move the cursor to approximately 0, 2, and that particular point right there, I'll kind of sketch this out over here. This is 0, 2. I'm looking for this minimum distance to the curve, which is probably going to be something like at a right angle to the curve itself. And because of symmetry, I bet we're probably going to find 2 different points. That looks to me like those would be the points at the minimum distance. So this point has the coordinates 0, 2. These 2 points would have the coordinates of some x and y value at this point. Okay? So that's what we want to minimize. Okay? Let's see how we can go about this. All right, now, distance. We're looking at distance in a plane, and we have a formula from the past which calculates distance from a plane. So the distance formula, the distance between any 2 points, is the square root of x2 minus x1, quantity squared, plus y2 minus y1, quantity squared. All right, so let's suppose then that we have to find the distance between the point 0, 2 and the point xy. Well, that we can do. We can calculate that distance by subtracting the x values, so x minus 0, quantity squared, plus y minus 2. Okay, and simplifying just a little bit, I could write this as the square root of x squared plus y minus 2 quantity squared. Now, this is a function for distance, and that is certainly the thing that we want to minimize. But just like with the area equation in the previous example, we don't particularly have a function of a single variable right now. We have a function of 2 different independent variables, x and y. Somehow we need to come up with a way of dealing with that and getting down to a single variable, because that's the only type of equation that we know how to solve at this point. Now, here's the trick. In this case, I calculated the distance between 0, 2 and xy. Xy can be the distance at any point on the plane. So this would give me a point, the distance between 0, 2 and any point that exists on the plane. But I'm not interested in any point that exists on the plane. I'm only interested in points that exist on that parabola. So my constraint is that the point xy exists on the parabola y equals 4 minus x squared. How do I make that happen? Well, it's actually easier than you think. To get the point xy to exist on the parabola 4 minus x squared, you just write your point as x comma 4 minus x squared. So your x value is independent. You can choose whatever you want for that. But whatever you choose, you have to plug it into the equation 4 minus x squared to figure out where the y value has to be in order to lie on the parabola. So I actually don't necessarily want the distance between my point 0, 2 and any point on the plane. I want the distance between 0, 2 and this one right here. I don't have to redo any work. All I have to do is just substitute 4 minus x squared in for y. So my new equation would look like this. D equals the square root of x squared plus 4 minus x squared minus 2 quantity squared, and simplify. So let's see, this would become the square root of x squared. 4 minus 2 is 2, so 2 minus x squared. Whoops, try that again. 2 minus x squared, quantity squared. And actually, I could probably do a little bit better if I went through and expanded this binomial, combined like terms, that sort of thing. So let me go ahead and do all that. So x squared plus, when I expand this binomial, it would be square of the first times, or plus 2 times the first times the second. So 2 times 2 is 4, times negative x squared would be negative 4x squared. And then the square of the second would be plus x to the fourth, which I can combine and rearrange terms and make this x to the fourth, x squared and negative 4x squared would combine to minus 3x squared and plus 4. So that's a much better function to work with because now it's just a single variable. And it turns out we can actually even do better than that. Here's the thing. The square root is a very predictable function. So everything underneath the square root, the square root function is what's known as a monotone increasing function. So wherever the square root of x to the fourth minus 3x squared plus 4 is going to have minimums and maximums are the exact same locations as where the part underneath the square root itself are going to have minimums and maximums. So we really only fundamentally need to work with, say, f of x. If I say d is the square root of f of x, then f of x becomes x to the fourth minus 3x squared plus 4. So I only need to really work with the part that's underneath the square root in terms of minimizing and maximizing. And that's a big advantage to us because we go from having to do chain rule derivatives of d to just power rule derivatives of f. And that only works because the entire function is, we're taking the square root of the entire function. All right, so let's start working with derivatives. So f prime of x would be 4x cubed minus 6x. And we want to know where critical numbers are. So if I take that function and looks like I can factor out 2x. So that would leave me 2x squared minus 3. So this would lead to a critical number of 0. This, let me work with a little bit and say, all right, so 2x squared minus 3 equals 0. Or 2x squared equals 3. So x squared is 3 halves. Or x is the plus or minus square root of 3 halves. Now, you absolutely can make that a rationalize the denominator, that is, and I think it would become square root of 6 over 2. It's not really all that big of a deal in calculus. It's usually something that you do in trigonometry, but you can leave it like this for all intents and purposes. Now, we need to determine of these critical numbers which ones are minimums and which ones are maximums. Because if we have any maximums, that's going to be a bit problematic. So we'd want to throw that out. And again, I think the second derivative test is probably going to be better than testing intervals with the first derivative test. So let's see. 12x squared minus 6 is my second derivative. So the second derivative evaluated at 0 gives me 12 times 0 squared minus 6, which is negative 6. So that's an interval that is concave down, and an interval that's concave down would have a relative maximum. So that's no good. That's going to make a large distance. We're trying to get a small distance here. If I plug in, say, the square root of 3 over 2, and you might be thinking that, oh no, this is going to be a headache, but luckily, look what happens. We plug it right into a square, and so the square root's going to disappear. And in fact, here's something that's even nicer. since we're squaring it, it really wouldn't matter. We could actually put the plus or the minus one in. Same thing's going to happen, because positive square root of 3 halves is just 3 halves, and the negative square root of 3 halves squared is just 3 halves. So this would be 12 times 3 halves minus 6. 12 goes into 2 6 times, so 18 minus 6 is 12, which is positive, which means we're on an interval that is concave up, and any critical number on an interval that's concave up would be a minimum. So both of these values here represent relative minimums. And that's what we're in fact looking for, because they're indicating these 2 points. We need to get the coordinates of those points, but they're indicating where those particular points exist. Now, what we just solved for was an x value. So this is the x value of where our minimum occurs. To get the y value, we just need to make sure that these y values appear on the parabola. So I go back to my constraint function, plug these into the constraint. So y at plus or minus root 3 over 2 would be 4 minus plus or minus root 3 over 2 squared. And I'm plugging in the positive and negative because when I square things, the positive and negative disappear. So just save me working out the problem twice. 4 minus 3 halves, which would be, let's see, 8 halves minus 3 halves, or 5 halves. So the distance is minimized at the points plus or minus square root of 3 halves, comma 5 halves. And if you want the minimum distance, then what you would need to do at that point is plug into this formula right here, which gives us the minimum distance. And let's go ahead and get that. The minimum distance is the square root of the plus or minus square root of 3 halves to the 4th power minus 3 times plus or minus square root of 3 halves squared and plus 4. A little bit of work with fractions, but won't be too bad, I think. Square root. All right, if I take this root, the square root to the 4th power, effectively what I would do is when I square it, it would make it 3 halves. Then I'm squaring 3 halves, and that would give me 9/4. So I have 9/4 minus 3 times 3 halves plus 4, or 9/4 minus 9 halves plus 4. And just bear with me for a second, working with these fractions. We'll get this done. Okay, so negative 18 and 16 give me negative 2 plus 9. That will give me the square root of 7/4. Since 4 is a perfect square, let's make it root 7 over 2. And that would be the actual minimum distance to those points. A manufacturer wants to design an open box to have a square base and a surface area of 108 inches. Square inches, sorry. What dimensions will produce a box with a maximum volume? So first, let's figure out what we want to maximize. So we want to maximize the volume of a rectangular well, it has a square base, but rectangular solid with a square base. So I'll just say rectangular or square solid. Okay. We've got an open. It's an open box, so we're not closing the top, but we do have a constraint. It's that the surface area is 108 square inches. Okay, so this box that I have, it's going to have a square base. All right, let's sketch that. All right, so there's my square base. Now, I know from squares that both sides have to be the same. So I'm going to go ahead and say that the dimension one direction and the dimension the other direction is x each way. So that's the same, and that's what makes it square. Now, I'm trying to make an open box. So this would just be the base of the box. I have to have sides as well. In order to have sides of this box, what I need to do is have basically like rectangular flaps like this that I can fold upward. All right, and when I fold those upward, that's what's going to make a box. And I'm probably going to ruin the picture of the box here, but once it's folded upward, I'm not great at drawing in 3D. That's what my box is going to look like. So the top is open, but each side is x and x, but having these flaps on the side allow me to fold upward to make the rectangular box. Okay, what's next? All right, so if I'm going to be able to do this, the thing that I am, well, let's look at it this way. I'm maximizing the volume of this this box. All right, so I'm going to have another dimension, which is the height of the box. So I'll call this side length here h, and if you'll notice, h has to be the same all the way around the box. So this distance along here is going to be that h, and it's going to be the same for all of those little rectangles on the side. Okay, now with that, we can say that the volume of this box, the volume of a rectangular solid, is going to be length times width times height. So length is x, width is x, height is h. So this is effectively x squared times h. All right, so we're getting somewhere. Let's see what else we can figure out here. All right, so that takes care of the function that we want to maximize. And as what's been happening, this is a function that has more than one independent variable. So I need to come up with a way of eliminating one of those variables with my constraint. So let's look at that constraint. The constraint is surface area. The surface area of this box, let's see if we can come up with that. So the amount of surface area on the bottom of the box would just be x times x, which is x squared. The surface area for each of those sides. So one dimension of these sides is h, the other dimension is x. So the amount of area in that side is x times h. So it will be plus x times h, but there's 4 of those. So it's not really just x times h, it's actually 4 times x times h. And all of those other rectangles have the same dimensions. It's x one way and h the other way. So we would always have x times h for each one of those. So 4 times x times h would be the total surface area of those smaller rectangles, x squared for the base. Here we are. We've got what we need. Now, there is a constraint on the surface area. It's that the surface area can only be 108 square inches. So 108 is x squared plus 4xh. What we would need to be able to do at this point is rewrite this equation so that we can get one variable in terms of the other variable. So for instance, if I subtract x squared from both sides, that's a start. But then to get h by itself, the next thing I would need to do is divide everything through by 4x. So that 4x will cancel, leaving me with just h. Now, 108 divided by 4, let's see if that divides evenly. I think it will. Yeah, it must. Let's see what it is. I think it's 52. Oh, 27. Good thing I used a calculator. So 27 over x is what that first part will reduce to. Then I have x squared over 4x, so I can write that as x over 4. Now that gives me something to write h in terms of x, which means combining these functions, the volume of this box can be found by taking x squared times h, which is 27 over x minus x over 4. And I can probably do some simplification here. So volume is 27x minus x cubed over 4. All right. Now, I need to maximize volume. And I can do that with this equation at this point because I only have one independent variable remaining. And so I can find a derivative of this volume equation. So that would be 27 minus 3/4 x squared. And when we are maximizing a function, we need to find out where its derivative is 0 or undefined, but often if you have polynomial functions, your derivative's not going to be undefined, so we don't have to worry about that here. I'm going to add 3/4 of x squared to both sides. And then I will multiply both sides by 4/3, because that will cancel this entire fraction. 3 goes into 27 9 times. 9 times 4 is 36. So x would be plus or minus 6. We can safely throw out -6 because it doesn't make sense that the side length of the box would be a negative dimension. So it's really just +6 that we need to make sure is resulting in a maximum. In order to prove that, however, we would either need to use the second derivative test or the first derivative test. And I think that the second derivative test is probably easier in this case. The second derivative of my function would be negative 6/4 of x, which is negative 3/2 of x. So that second derivative evaluated at 6 would be negative 3/2 times 6. 2 goes into 6 3 times. We end up with negative 9. On an interval that, well, if my second derivative is negative, that means I'm on an interval that is concave down. And an interval that's concave down, if we come across a critical number, it's got to be a maximum. So this point of 6 will maximize volume. So what I need to do then is go back to my original problem here. I'm trying to find all the dimensions. So I know that the base dimensions of the square are 6 and 6. I need to come up with the height. So the height of the box, if the base is 6, would be 27 over 6 minus 6 over 4, which, let's see, 6 goes into 27. They share a factor of 3, so 9/2 minus 3/2, which would be 6/2 or 3. So the dimensions of the box would be 6, 6, and 3. And then the volume, the maximum volume, would be 6 times 6 times 3. 36 times 3, 108. And this would be cubic inches. I guess each of these I should have put inches on. But this will be cubic inches since it's a volume.